the result remains same, sir. In that case, sir, overflow plug is 1, just similar to the last one.
Firework flag is on. What is the reason? Here.
Sir, after completing the 2s complement, sir, the
Hmm.
result is same.
So why it is on? What is the reason? The result is same, but if the result is same, then why overflow become one? Yeah, so result is same. You can see. So when you make a number negative, suppose if you make negative plus five negative, then what will get result? If you make plus five negative, then what will you get?
Sir, minus 5, sir.
Yes, so you'll get minus five definitely. Suppose if you make negative minus eight, then what will you get?
Then plus 8, sir.
Plus eight. Okay. So if you make negative minus 8 কে যদি আমরা নেগেটিভ করি তাহলে আসে কি মাইনাস মাইনাস 8 তার মানে হচ্ছে চলে আসবে প্লাস 8 সো এখানে প্লাস 8 চলে আসছে আবার যদি প্লাস 5 কে নেগেটিভ করি তাহলে আসবে মাইনাস 5 so when you make a number negative so you expect what you expect a sign change right
Yes, sir.
sign
Opposite
change
sign, sir.
yeah you should get opposite sign but here the thing is you know that MSB represents sign for binary number you can see in the binary MSB is same or different.
Sir, same, sir.
Yeah, so MSB is same. So you can see this is the original number, MSB1, that means negative number. If you come here, that is also MSB1, that means that is also negative in sign number.
Negative number. Yes,
So
sir.
in sign number, if you make a positive number, choose complement, you'll get negative number. You get negative number, choose complement, get positive number. So there are some number, this is the special number. So in that case, there is no sign change. So you expect a sign change, but there is no sign change. That's why OF equal 1. Okay.
Yes, sir.
So OF equal 1 because after making two's complement, we expect a sign change because after making two's complement, we expect a sign change, but there is no sign change. Okay, so there is no sign change. So we expect a sign change, but actually there is no sign change. That's why OF equal 1. Then after that,
Sir, sign flag is on because MSB is on.
sign flag equal 1 because the result is negative. Okay, then
Sir, zero flag. JTAP is
J,
equal to 0, sir, because result is non-zero.
ZF equal 0. Result is non-zero, right? Yes, there is no carry, so result is non-zero because the non-zero. And then after that,
Sir, auxiliary flag, sir.
OF. Oh, we have already taken. Wave is the overflow.
Sir, AF, sir.
Auxiliary carry flag. AF. Okay, auxiliary carry flag. So is it
Sir,
one
carry it out
or
from the 3-bit. Yes, sir, one, sir. Because of, sir, carry it out from the 3-bit.
yeah? So there is a carry out from bit three. Okay, so one. Bit three. Okay, then
Sir, carry flag on, sir.
flag one or zero.
On, sir. Because of
Why?
yeah, carry it out on.
কই carry out কোথায় এখানে?
Sir, for the two's complement, sir, we are always expecting the one, sir.
না 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 সেটা বলা যাবে না। ক্যারি আউট তো নেই। ক্যারি ফ্ল্যাগ আমাদের এখানে চুজ কমপ্লিমেন্টের জন্য তো সাইনের ক্ষেত্রে যাচ্ছে। এখানে তো আনসাইনের নাম্বার। ওকে, সো এই যে আপনারা রুলস ভুলে গিয়েছেন। সো রুলস মনে রাখতে হবে। সো ইউ হ্যাভ টু রিমেম্বার দ্য রিজন। You know this is one, but you have to remember the reason for that. So last class we studied that. You can say move, exchange, affect flag none, add sub, affect flag all, increment, decrement, all except CF, and any G. Okay, neg. This is the operation we're talking. So all CF equal 1 unless result is 0. Wave, okay, wave or CF. Wave equal 1 if the word operand is A000. Look, so wave equal 1, it should be wave equal 1. CF equal 1 unless the result is 0. So there is no carry here. Still CF is 1 because result is not 0. Understand? CF equal 1 not for the sign change, sign not changing. CF equal 1
Yes,
because
sir.
the
It's a
result is
condition,
not
sir.
0. It's a condition only applicable for any G operation.
Yes, sir.
Got it? So CF equal 1 unless the result is 0, and that is the only applicable condition for, I
Sir,
think,
if the result is, sir, non-zero.
yes, CF equal 1 if the result is non, yes, CF equal 1, that is zero flag এর মতন একটা হয়ে গেছে, তাই না?
G, sir.
উল্টা জিরো ফ্ল্যাগের উল্টা হয়েছে, এটা জিরো হয়। So CF equal 1 unless as the result is non-zero. So as the result is non-zero, CF. Okay, whose one is left? One, two, three, four, five. Oh, okay, what about PF?
Sir, even, sir, one, sir.
Why?
Bec- because of the, sir, lower byte is event parity, sir.
Okay, so low byte is even better, you can see. So here people one of the low byte even parity. Okay, so you can take screenshot. So we're going to end this session. and we'll come back. We'll come back.
স্যার লাস্টের পেজটা একটু দেখি না স্যার, একটু স্যার একটু। ওকে স্যার।
Okay, so we are close to the end of chapter 5. So chapter 5 is a small chapter. So you can see here. Okay, so we already completed this example 5.1, example 5.2. Three, four, five, six. Okay. The debug program. The debug program provides an environment in which a program may be tested. User can step through a program and display and change the register and memory. It is also possible to enter the assembly code directly, which debug converts to machine code and store in memory. A tutorial for debugging could be a more sophisticated debugger may be found in Appendix C. We use debug to demonstrate the way instruction affect the flag. To the end, the following program has been created. Okay, we have a program here, so you can run that program by MOH86 and you can check the flag register for what is the value of the flag register. You can check that, and yeah, so this is the end of chapter 5. Actually, we have finished this problem, example 5.6, and after that we have a program here, sample program to test the flag register. You can test that by MOH86. This program. Okay, so this is the sample program given to test the value of the flag register. You can see after each and every step, the value of flag register will change according to the output of the program. So this is the first step. And this is the second step. This is the third step. This is the fourth step, fifth step. And for each and every step, the value of flag register will change according to the program. You can check that. You can go in and check that. Okay, so they have given this code here. Yeah, last code is also giving you, you can see. Okay, so this is their code to check the flag register value, how the value changes. So that is the first line, then add into and main. Okay, so this is the code. So you can check that. So what is the value of flag register? So you can find flag register here. So look, the program is not pointing to the .model small .stack 108 .code main program is pointing to the code. You can see the yellow color line, move x comma 4000. That is the starting line. So that's why the program is pointing to that line. Okay, so look at here. So all the flags right now 0. All the flags right now 0. So we have CF carry flag 1, 2, 3, 4, 5, 6, 7, 8. We have 8 flag here, you can see, and we are going to talk about this CF, ZF, SF, wave, and PFNA. And these two are control flag. So inter flag is enabled right now because without inter flag being enabled, you cannot run the program. That's why. Okay, so these first six flag, these are our discussion. So these are status flag. So now we're pointing to the first line, move x, comma 4000 hex. After running this code, your flag value will definitely change. So let's run this first line single step and let's see how the value changed. Okay, we run the first line, move and no change. You can see because move operation, you already know that move operation does not affect any of the flag. So that's why when you run move x, 4000 hex, all the flag will remain the same. Okay. After that add operation, you know that add operation affects all of the flag, and depending on the result of your add operation, some flag will be changed. So you perform the add operation. Now let's see what is the value of the flag. You can see the CF remains 0, ZF remains 0, SF changes to 1, WF changes to 1, PF changes to 1, AF remains 0. So these three flags change to 1 because when you add operation, you can check that it is given in the book, chapter 5, this program. Then you can analyze why it is become 1 and 1, 1, 1. That is what you can do by yourself. Okay, so you can check that. Then if you press single step again, so we are at this line sub x comma 0 FFF. So again, you know that sub operation also affects all of the flag. So some flag will change. So we perform that. So look, now the flag value changed from the previous one. So you get CF equal 1, ZF equal 0, SF equal 1, and F equal 1. And okay, let's see. So this will also change. So then we are at neg operation. Let's perform it, neg operation. So then press single step. You may see some, yeah. So there are some changing you can see. So now ZF, SF, and Web 0. Now we are at increment operation, and let's see, perform it, and then it will change. Okay. So then we are at the end, move S, 4, CAs, and 21. Okay, so this is the code you can find in chapter 5. So you can play with that if you want. So this is the code given at the chapter 5 at the end of the example 5.6, example 5.6. Then we have this code, so you can check there from chapter 5. And that is the end of chapter 5. That is the end of chapter 5. So you can see the summary
Sir,
here. Yes. What?
sir, will it show the all the flag for each operation?
I don't understand. What did you say?
Sir, I want to say, sir, for add
Mm-hmm.
operation. So, sh- sir, will we, sir, will we determine the for six flag from this
Yeah.
add operation?
Yes, yes. So these are the operation here. You can see after positive. These are the operation. So if I give you a program, then you determine the each and every flag for the given operation for each and every step. Okay. So that is the end of chapter 5. So we have some exercise in chapter 5. You can solve that. Okay, please solve by yourself. So at the end of the chapter 5, you can see there are exercise. So it's continuous. It's continuous. So there are many exercises. You can go through that if you want. So up to this. Okay, so that is the end of chapter 5. So we're going to start a new chapter today, and that is chapter 9. Chapter 5. Chapter 5. Okay, we studied chapter 3, right? Right, chapter 3, 1 to 3. This is chapter 3. Yeah, we started chapter 3, but chapter 3 is not related to programming. So this is actually the architecture. In the architecture, I think we studied this chapter, but we did not cover the, I mean, this kind of evaluation of Intel microprocessor. So you can read that. So when you get evaluation of Intel microprocessor from chapter 3, so 8086, 8088, then 80186, 80188, 80286, 80386, 80386 SS, 80486, 486 SS. Then we did that. These are the data register. We already discussed that because we discussed chapter 1 in very details, and that's why I think we already covered in chapter 1. So you can see these are the register of 8086 microprocessor. We already covered in chapter 3, but we already covered that in chapter 1. So data register, segment register, 4 segment register, pointer and index register, 5 pointer and index register, and flag register. So and these are the description of each and every register and what they perform. Then I think we discussed this part of chapter 3, previous before midterm. Yeah, we discussed this part. So the address, memory address, then the memory segment is to offset address. We already discussed those. Location of segment. We already solved example 3.1, 3.2. That is what we also solved. So physical address equals segment equal 10 plus offset. Then there are some pointer registers. You can study that. This pointer, stack pointer, source pointer. These are the registers. So these are the chapter 3 is about the organization of processor, how the processor works, what are there in the processor. And after at the end of the chapter 3, you have some exercise. You can solve that exercise. Please solve exercise 1, 2, 3, 4, 5, 5, 6. But we already discussed those. What is paragraph boundary? Suppose we already discussed that. Please solve those. Okay, so that is chapter 3. So we already discussed chapter 3. Okay, so multiplication and division instruction. This is a new chapter. So, okay, chapter name is multiplication and division operation. Multiplication and division operation. So what it says, okay, let's start this chapter. So I don't want to study the overview. So let's start from here. Okay, so sign versus, okay, multiplication. So you can see the syntax is MUL and IMUL. So you can see there are two types of operation. One is signed and another one is called unsigned operation. So there are two types of operation. One is signed multiplication, other is called unsigned multiplication. So what it says, in binary multiplication, signed and unsigned numbers must be treated differently. We always treat signed and unsigned number differently, whether it is any kind of arithmetic operation, whether it is addition operation, subtraction operation, multiplication operation, or division operation. We always treat signed and unsigned number differently, because the signed value is different, the unsigned value is different. So if the number is positive, in that case, the signed value and unsigned value is the same. But when the number is negative, that means MSB is 1, the signed value and unsigned value is different. That is what you have to remember. So signed and unsigned numbers must be treated differently. For example, suppose we want to multiply 8-bit numbers. Suppose if you want to multiply 8-bit numbers, this number and this number, you want to multiply these two numbers, interpreted as unsigned number, they represents 128 and 255. So 10000000170 equal 128 in unsigned case, and 111181 equal 255 in unsigned case. Then the product will be 32764. You are multiplying 255 with 128. The product is 32640. However, taken as signed number, if you think them as signed number, you know that signed number is different because both are negative number for signed case, because they are MSB. For both case, here you can see the MSB is 1. Here you can also see that the MSB is 1. So that means if you consider them as a signed number, they both will represent negative number. But for unsigned case, they both represents the positive number, because you know that from chapter 2, the unsigned number always starts at 0 and goes up to the last number according to the whether you works with the bit or byte, whether you works with byte or word or double word or quad word. So unsigned number always starts at 0. That means unsigned number is always positive. So 0 then 1, that means it will be always positive. So 170 equal to 128, and all 1 indicates 255 in unsigned case. That's why the product will be 327,640. However, taken as sine number, if you take them as sine number, they represents minus 128. The first number represents minus 128 and the second number represents minus 1. Okay, the first number represents minus 128 and second number represents minus 1 respectively, and the product is 128 because you know that minus 128 into minus 1, then it will be what it will be. This is the product. So plus 128 because if you multiply minus 128, but it's very simple, right? So, but the tricky thing is you have to find out whether the value, what is the value. So that is the tricky thing. But multiplication is simple. So because sine and unsigned multiplication leads to different result. So sine and unsigned multiplication leads to different result, not the same result. Because sine case the result is 32640, and for unsigned case the result is 128. Totally different results. There are two multiplication instruction MUL, MUL for unsigned multiplication. MUL means multiply, and that is for unsigned multiplication. That is the syntax. So what is the syntax for unsigned multiplication? Unsigned multiplication syntax is MUL. MUL means multiply. So, and signed multiplication syntax is different because the signed result is different. So if you multiply signed number, then the result is different. And IMUL, integer multiply. IMUL means what? IMUL means integer multiply for what? For sign multiplication. For sign multiplication. So what is the syntax for unsigned multiplication? The syntax is unsigned multiplication is, operation is MUL, means multiply, and sign multiplication, IMUL, that means integer multiply for sign multiplication. So this instruction multiplies byte or words. So they can multiply byte or words. So we are not going beyond the words. Word means, you know, the 16-bit. We are not going beyond the word. Beyond the word means 32-bit or 64-bit. So we are not discussing that because we are dealing with the 64-bit processor. So we are dealing with the 16-bit processor. For 16-bit processor, the highest limit is the word. So this instruction multiply bytes or words. If 2 bytes are multiplied, the product is a word. If 2 words are multiplied, the product is the double word. So if two bytes are multiplied, the product is a word. That means the product is 16-bit. When you multiply 8-bit into 8-bit value, then the product will be the 16-bit. If 2 words are multiplied, that means if you multiply 16-bit and 16-bit, the product will be a double word. That means product will be a 32-bit. The syntax, what is the syntax? Syntax is a way we write the instruction to perform that instruction. So in assembly, we write that MUL source. There is no destination here. You can see MUL source, that is the syntax for unsigned multiplication, and IMUL source, that is the syntax for signed multiplication. Okay. So the syntax for unsigned multiplication is what? MUL, then space, then source, and the syntax for unsigned multiplication is MUL space source, and the syntax for signed multiplication is IMUL source. Okay. So let me ask someone a question. So yeah, so who can answer? Okay, Salman Khan. Salman Khan, how are you? Okay, tell me. Okay, good. So tell me, what is the syntax for sign multiplication? IML, then you have to tell the full form. Space. Then operand, কোন operand দিব ওখানে? Destination or source? Source. Good. And what is the syntax for unsigned multiplication? Okay, good. So those are the two syntax for two types of multiplication. Okay. Now multiplication, we will see two form. One is byte form, other is word form. So two form are there. One is byte form, other is word form. And we will not discuss the double word form, but if you understand byte form and word form, you will understand how the multiplication operation are performed in 64-bit processor. Those are similar things. But 64-bit is, you know, that is the quad word. So we are not going to discuss quad word. So here we only discuss byte and word, but everything is same actually. So for byte multiplication, one number is contained in the source and other is assumed to be in AL. So for byte multiplication, what it says for byte multiplication, one number multiplication, for multiplication we need two number, but in our syntax you can see, in our syntax we have only source, there is no destination for multiplication. Like for addition operation, you have seen that previously in chapter 4, that we have destination and we have source. But here you can see the interesting thing is, for multiplication you need two number, because how can you multiply by one number? You have to multiply two number together, or three number, more than two number. So but here you have only source, there is no destination, so you cannot multiply one number, only one number, right? So you can multiply one a number with itself, that is what, but still you need to store the same number in the other register, but there is no source here, there is no destination here. But destination, you don't have to take the destination, that is the wrong. If you take write multiplication x comma bx, or if you write multiplication x comma 5, so that will not work. So that syntax is totally incorrect. Here the processor itself will automatically assign the destination for you. You don't have to take any destination. The processor itself will automatically assign the destination for you. And when you perform the byte operation, the processor itself will assign you the destination AL. So you don't have to worry about that. So the byte multiplication, the one number is contained in the source. One number you will write the what number you want to put, so that will put in the source, and the others is assumed. Look, assumed means ধরে নেওয়া, to be in register AL, that will automatically processor will keep in register AL.
Sir, is it fixed, sir?
Yeah, it is the fixed register, so that's why the other number will always processor will keep always in register AL, so you have to look at register AL always. So you cannot it cannot be kept in another register, so it will automatically keep in register AL for 8-bit
Sir,
operation.
because of because of we are calculating the 8-bit number.
Yes, we are working with 8-bit number.
Yes.
Yeah, where and the product will, we already said that when you multiply two 8-bit number, the product will be 16-bit. If 2 bytes are multiplied, the product is a word that is 16-bit. So that means when you multiply one number, you are keeping at source will take, you take bx. You cannot you can also take al. I think it's better to take other register for source, like bx or dx.
Sir, here AL is considered as a destination, sir. Is it, sir?
Yeah, so AL is not like destination. Okay, you can say it destination, but it's not like destination. It is keeping the other number. So for multiplying, you need two number, but destination is not in your operation. You are not giving the destination because you are
So
writing MUL source. I mean, you are writing MUL.
yes,
Suppose you are writing MUL BX, MUL BL for 8-bit. Then you need another number, right, to perform the multiplication. So other number will
yes,
be
sir.
stored in L. That is automatically
So,
stored in
so
L.
question is that, sir, the result will be stored in where, sir?
Okay, that is what I'm saying now. The 16-bit product means result. The 16-bit product will be in AX. Okay. Okay. The
Yes,
16-bit, because when you multiply 2 byte, you get 16-bit product. Remember that. If you multiply 2 word, it is written here, then you'll get 32-bit product. If you multiply 2 double word means 32-bit. If you multiply 2 32-bit, then you get 64-bit product. If you multiply 2 64-bit,
yes,
you'll get 128-bit product. The source may be a byte register. Source can be byte register or memory byte. Memory byte means variable. Source can be a byte register or source can be variable, but not a constant. You cannot keep source constant. That means you cannot write. You cannot write. You can write this one, mul bl, or you can write source is also, you can write memories, like suppose mul word byte 1, byte byte 1. That is what you can write in source, and byte 1 is a variable. You have to assign that variable. So first you have hopefully you can remember how we assign byte 1 variable from chapter. Okay, so byte 1 you have to assign from chapter 4. You know that how we assign byte 1, byte byte 1 db. Hopefully you can remember, and question mark uninitialized. Okay,
yes, sir.
so you can
I
write
remember.
that, but you cannot write source cannot source cannot be constant. But that means you cannot write mul constant, or you can also cannot write number like mul 128. So you are multiplying 128 with whatever value in L. You cannot write that. So you have to
Yes,
keep 128 in BL. Then you can write BL here.
sir. We
Okay,
can
so that is
write the source as a register or memory location.
exactly. That is what I am saying.
Sir,
Uh,
sir, in that, sir, in the byte form, we are working with, sir, 8-bit. The result will be, sir, 16-bit. That's why it will be stored in AX.
mhm.
Sir, for the case of word form, we will work with, sir, 16-bit. So, sir, result will be, sir, 32
32-bit.
bits, sir.
Yes.
So, sir, result will stored where, sir?
Oh, yes. So we are working with, the 16-bit processor. All the registers are 16-bit. You already know from chapter 1 and chapter 3.
Yes,
Here
sir.
all the registers are 16-bit. That's why, 32-bit, to store 32-bit, you need two registers. And
Oh,
can you
yes.
remember that in chapter 3, we studied this, chapter 3, I think. Okay, where is chapter 3? 1, 2, 3. Okay, let me go to chapter 3. Okay. Okay, here you can see in chapter 3, when we discuss register. Okay, so here in dx. Okay, it is written here. Can you see what is written here for dx in chapter
Sir,
3?
yes, sir. It is used for multiplication and division, sir.
Yes. So for 16-bit, it is going to register X, but when you said when the result will be 32-bit, what will happen? Then 32-bit, lower part, lower 16-bit, lower word, 16-bit is called word, right? So lower word will go to register X, and higher word will go to register DX. That's why it is written,
Yes, sir.
DX is
Yes.
multiplication and division operation.
Yes, sir. I got the answer, sir.
Thank you. So let's see that 16-bit, then you'll understand that. So for word multiplication, one number is contained in the source and other number is assumed. That is what you are not writing, but you have to assume that is other number is in register X.
X. Yes, sir.
The most significant of 16-bit of the double word product. Okay, so এখানে বলতেছে যে যখন আমরা প্রোডাক্ট পাবো সেটা তো ডাবল ওয়ার্ড হবে। সো ডাবল
Yes.
ওয়ার্ডের হায়ার ওয়ার্ড, সো এখানে দুইটা ওয়ার্ড থাকবে, তাই না? একটা হচ্ছে লোয়ার ওয়ার্ড, একটা হচ্ছে হায়ার ওয়ার্ড।
Higher
সো
word.
হায়ার ওয়ার্ডটা চলে যাবে, প্রোডাক্ট অফ হায়ার ওয়ার্ড উইল বি ইন রেজিস্টার ডিএক্স, and the least significant 16 bit. Least significant bit 16 bit means lower word. So lower word
Lower
will
word.
be in X. Okay, and we
Yes, sir.
can write that in form dx into X. So because all registers are 16 bit, you cannot store the result in X. Then it will get overflow, but we don't want overflow, right? So
Yes, sir.
what can we do? We can store lower 16 bit in X, and we can store higher 16 bit in DX. The source may be a 16 bit. The source may be like before. The source may be a 16 bit register or
Register or memory location.
memory location, memory word here, because it is a word variable. You
Word.
have to take word variable for source
Yes, sir.
because
Yes,
you
sir,
Word
are,
variable.
but not a constant.
but not a constant. Exactly. Now for multiplication of positive number, 0 is the most significant bit. The 0, if you multiply positive numbers, then
Sir,
0,
4
0
minutes
is,
left.
okay, then up to, we can keep up to this. We'll come next class and we'll
Yes, sir.
see. Okay, thank you.
For attendance,
Oh, okay. Time 10. Okay, please respond. Sabir
sir,
Rahman.
time 10 to 12, sir.
Okay, got it. So Sabir Rahman, absent. Okay. Aslam. আসলাম তো ছিল মনে হয়। তাসনিম হুসাইন রাফি,
Yes, sir.
ফিরোজ, আনিসুল, আজিজুল ইসলাম,
Present, sir.
প্রসঞ্জিৎ,
Sir, Azizul
Shaman.
Islam present, sir.
Yes, sir. Yes,
Okay.
sir.
Hafiza, again Hafiza.
Yes, sir.
Who is one present? Empty.
Yes, sir.
Okay, Mohaminul.
Sir, present.
Okay. So Mohaminul,
Sir, ও আছে স্যার।
Ibrahim,
Present, sir.
Sujan, Nahid Hassan Ridoy,